here we have construction of a power function, exponential function for both the positive and the negative doubling displacement, and the sine function, and a couple of comments about the algebraic properties. So here I've constructed a power function, haven't actually constructed it, I've sketched it, with a y factor of 4/3. Now, this means what? That the y value, as we go from one to another of a series of doubling x values, changes by a factor of 4/3. Restating it, we have a series of doubling x values here. From every x value to the next, the value of y changes by factor 4/3. Now, we know that we can't actually construct a factor 4/3. We can only, well, we can construct, we know we can construct y factors of the form p over 2 to the n, rational numbers with denominators that are powers of 2. We established that early, and I'm not going to go through the details of that. You can review some of the previous videos, some of the original videos. But we know we can't trisect a line by geometric construction. So what we do is, though, we actually start with this value and work backwards, so that this line is 3/4 of the length of this line, or this value is 3/4 the length of this value, and we can do that easily. We just bisect this segment and then bisect this remaining segment and take this much of it, and here is our previous value. And we can keep doing that all the way back. We also have established that if we continue this process back toward the origin, we will approach y equals 0 as a limit, provided your y factor is such that the graph is increasing. That is for a power function. So I've been able to construct at least these points with the ratio of 4/3 on a finite part of the x-axis, which includes or goes right up to x equals 0. But I can't continue it from here on, not with geometric construction. I can't construct a line that's 4/3 the length of this one. So this is constructible only on a finite domain. If we decide we want this much of the x-axis, then we can start here, put a point up here, and work backwards. If we want to work forwards, it's extremely helpful to have a denominator that's a power of 2. We know that we can always do that. There are other factors that can be constructed. We've looked at them. Certain square roots, which are irrational numbers, can be constructed just by constructing right triangles. But that isn't going to help us construct a 4/3. It can be mathematically proved that 4/3 is an impossible ratio. So there's a little extra. But this should refresh you on how we construct a power function graph. This is meant just as a refresher. Details are in original videos. Exponential function. How do we construct an exponential function? Well, we start with an arrow that represents a doubling displacement at an x-axis. So we put a series of these arrows head to tail along the x-axis, and we choose a beginning value. We move over through the distance of that arrow and double the y value. Move over again, doubling the y value. Move over another arrow, double the y value. Move over another arrow, dot, dot, dot. And that gives us a graph that looks very much like this. Now, the doubling displacement could also be negative. So if the doubling displacement has the same magnitude, in other words, if it involves the same distance but going in the other direction, that means that if we start here, we've got to move this way to double. And then we've got to move this way, double again, move this way, double again, and so forth. And we get a graph that looks very much like this for negative doubling displacement. These are both perfectly valid exponential functions. Another thing is that we can put the y-axis anywhere. We didn't need a y-axis to do any of this. And now if we decide we want a y-axis wherever we decide we want it, let's say right here, then we've got it. If this is our basic exponential function, if this represents y equals b to the x for some b, then we get a bonus. We actually have a scale for our y-axis. If we wanted the scale to look differently, we could move the y-axis to the right or left. If we wanted the unit 1 to be a little smaller, of course, we have two different graphs with two different points, 0, 1. This would also be a point 0, 1 here on this graph. So for following the orange graph, this yellow 0, 1 would be our y-intercept. If we're following the white graph, then the point 0, 1 would have to be here, and of course we would have two different scales for our two different exponential functions. But for any one of these exponential functions, we'd have just a graph that represents that function. And as we've seen, we can always double label an axis if we have a reason to do so, as long as we keep straight which labeling means which. Okay, well, don't want to go much deeper than this, just refreshing your memory and maybe pointing out a couple of things that you might want to think about. Okay, sine function, we start with a circle. We put an x and y, an xy coordinate system through the origin, and then we kind of extend our x-axis here to an x-axis for our graph. Now this x-axis isn't the same for this x-axis as this x-axis. It could be labeled in different units. It could have a completely different scale than the x-axis for our reference circle. So we have an xy coordinate system here, an xy coordinate system here, and they don't have to have the same scales, especially for the x-axis. Now it's convenient if the y-axis has the same scale, so that we can, well, do what we're going to do here in a minute. So in order to construct the graph of the sine function, it's actually quite simple. We simply take the angle from the positive x-axis to the positive y-axis, and we bisect that angle, getting this angle, which gives us a point on the circle. We project that point of the circle over to the y-axis, and we mark that point. Then we take the angle here and bisect it, getting this angle, giving us a point on the circle. Project that point over to the y-axis and mark that point. And of course we got a point here at the positive x-axis, and we mark that point. And then we bisect the angle between here and here, getting this angle, and we project that over to the y-axis. And then we take the point that where the circle actually meets the y-axis, and we mark that point. Okay, now these points, this point, 1, 2, 3, 4, 5 points on the circle are equally spaced along the circle. The distance along the arc from here to here is the same as from here to here, same as from here to here, same as from here to here. That didn't draw it perfectly, so it doesn't necessarily look that way, but that is the way we construct it. Then we start by marking off 1, 2, 3, 4, 5 points on the x-axis here, corresponding to 1, 2, 3, 4, 5 points on our circle. And to each point we associate the y value. So for this point, here's the y value. Well, this point corresponds to x equals 0, and corresponds to 0 on this x-axis. Of course, the x-coordinate isn't 0 here. The x-coordinate here is actually the angle here. So we take this coordinate, associate it with the 0 angle, and put it here. Then we take this coordinate, associate it with the next increment of angle, and put it here. And then this coordinate, which we'll associate with this angle, Well, that would be this angle. That goes here. And then this coordinate with this angle gives us a point here, and this coordinate with this angle gives us a point here. We can then sketch a smooth curve. Then we ask ourselves, well, what if we keep going around the circle? Well, clearly, we could subdivide the angle from the positive y-axis to the negative x-axis the same way we did previously, and we could consider that we just keep going around the circle in the same direction that we started, and we're just going to repeat these y values, meaning that the graph from here to here is going to be symmetric. If I draw it that way, I kind of messed that up. But it should be symmetric about a vertical line through this point. And then if we subdivide this right angle into 4 pieces, we get the same y values but negative in the same order that we got the positive y values here. And people on the final had no problem doing this and saw that, okay, well, now the graph goes like this, and I'm not drawing it very well. And then as we go from here to here, the y values again repeat, but going back up to 0, and we complete a cycle of the sine function. Now, they're algebraic relationships, but I've gone on a little longer than I anticipated, so I'm going to stop this video and then talk about these ideas more briefly in another video.